So there's only one slide that goes with this. This is it. Projectiles launched at an angle. The initial velocity has an x and a y. The v sub x is constant because we have yet to strap a rocket to the butt of anything, nor will we in this class. That's beyond what we want to do. We don't want to do that. So everything that we're looking at, because they're projectiles, is moving only under the influence of gravity. And if it's moving only under the influence of gravity, the velocity on the y-axis is changing every millisecond, but the x is constant, and boy is that important because it gives us something to hang on to, in essence. Vy does change. And if we've got very, very often with these, we're looking at things that are being described from the horizon. So the most common setup for these is that the sine of theta gets you your y-axis and the cosine gets you your x. I would advise draw the picture, draw a little line. I can't think of one where it's not as that, but it could happen. So if we look at that, let's just look at a generic object. So potato cannon, launched from ground level. If this thing is launched at an initial velocity of 76.0 meters per second, really screaming, lots of hairspray, lots of Aquanet. What is the initial velocity on the x? What is the initial velocity on the y? I didn't even give you a number for the angle, so you can't give me a number back. What you can give me is an expression. And that expression is what you're going to start listing as a variable. So at this point, when you start setting up the equation and you go to list the variables, your VIX and your VIY, you're going to put in expressions in your variable list. There are very good reasons for not solving for it right away. Very often, again, we're doing algebra with it and we're eliminating that trig function, or we're solving for VI by taking cosine and moving it around. So we don't want to solve for that. We want to leave it as an expression. Okay. That's really at the heart of what we're doing. Everything that we have done with horizontally launched projectiles, we're going to do here and a little bit more. But the critical difference is that now, every single time, you're going to have two initial velocity expressions, and they're going to be separated. 103. So, zookeeper, and I don't like the way they do it for a couple of reasons. I think we'll talk about that in a second. Zookeeper finds an escaped monkey hanging from a light pole, aiming her tranquilizer gun at the monkey. She kneels 10 meters from the light pole, which is 5 meters high. Tip of her gun is 1 meter above the ground. The monkey tries to trick the zookeeper by dropping a banana, but then continues to hold on to the light pole. At the moment the monkey releases the banana, the zookeeper shoots. If the tranquilizer dart travels at 50 meters per second, will the dart hit the monkey or the banana or either of them? So we'll draw our little picture. Okay, so what we know is that uninterrupted, that tranquilizer dart will rise and fall. And all you've done is take the two kinds of one-dimensional motion and put them together. So you had this kind of one-dimensional motion and you had this kind of one-dimensional motion. And if you add them together, what you get as a sort of sum is that. What we're interested in is at the 10-meter mark here, what point in its flight is that dart at? Because for every single moment in its flight path, there's an x and a y component, and there's a time for every single point in the flight path. The first thing we want to do is what? List variables on the x and y axis. Yes, sir. Yes, please disregard the insane person up front. Thank you. X and y are switched. I do count on you guys to keep me some semblance of sane. There we go. Thanks. Just keeping you on your toes, that's what I'll say. Yeah. So we have an x and a y velocity. Okay, the first thing we want to do is, of course, list our variables on each axis. So I'm going to shrink this. I'm going to get rid of that. Okay, so for VIX and VIY, we're going to create expressions. We have an angle theta, which we don't know yet. I'll set that over here. But we know that VIX is going to be the cosine of theta times VI. And we know that VIY is going to be the sine of theta VI. We know that there's no acceleration on the x-axis. That's a 0. That's just going to be dismissed. Acceleration on the y is going to be negative 9.81 meters per second squared. You want to be really careful. Too hard to read? Okay. You want to be really careful with your delta x and your delta y. Remember all the problems where they give you some distance and it's not your delta y or it's not your delta x, you're just comparing it? We don't know what the delta y is at 10 meters here. That's really what we're interested in. We know how high the monkey is, but we don't know if the dart strikes the monkey or not. What we know is that we're interested in where on the y-axis it is when delta x equals 10 meters. Delta t is, of course, going to be the bridge that connects the axes. So we can do the same thing we've been doing, we just have to do it a little bit more carefully, because no longer is our VIY 0. So we can do this. Delta t is equal to, delta x over VIX. That's still true because there's no acceleration on the x-axis. So that's still a true substitution. The substitution that a lot of you have been using in the other problems where on the y-axis t is equal to the square root of, 2 delta y divided by a, that's no longer true. That doesn't apply because VIY is not 0. So you cannot use that derivation anymore. What we can do, though, is say, well, we've got VIY, we've got acceleration on the y, we've got an expression for delta t. We're now interested in getting delta y. Do we have an equation that ties those together? Of course we do. We've been using it a lot. It's my favorite of the kinematics. I don't know why. Delta y equals VIY delta t plus 1/2 a delta t squared. So this is a good time to put in our expressions for VIY and VIX. I'm going to move this down and out of the way a little bit. So what we're saying here is that delta t is delta x over cosine theta VI. What we're saying here is that VIY is sine theta VI. So delta y equals sine theta VI delta t plus 1/2 a delta t squared. We're ready to do some manipulation here. We're going to take just this and we're going to carry it to the next page. And actually I'm going to line these up a little bit differently. So of course you know that we're going to take this and substitute it in for delta t. This is basically the same thing we've been doing. So we now have delta y equals sine theta VI times the quantity delta x over cosine theta VI plus 1/2 a delta x over cosine theta vi squared. We're just down to algebra at this point. And actually not even a whole lot of that. We're just solving for delta y. Is there anything we're missing? Anybody want to throw a flag on this play? Woo! I used a sports metaphor. That never happens. I try. They're apt to be muddled. Nobody? What's theta? We don't know theta. We can find theta easily. So if we back up to here and we note, we are told that, let me see if I can just copy that piece. We're told that she aims the gun at the monkey. So the distance, she is 10 meters away. So this is 10 meters. The tip of her gun is a meter above the ground and the monkey's 5 meters up. So this is 4 meters. Now do you have a way to find theta? What function? Tangent. Yes, inverse tangent. Of 4, yeah, inverse tangent of 0.4. Inverse tangent of 4 divided by 10 will get you your theta. A reminder, keep all those digits. So tan minus 1, 4 over 10 equals theta. So we end up with this tangent of 21.8, etc. Keep it in your calculator. You don't have to write the whole thing down, obviously. So at this point, are we ready to solve, having tangent? Let's plug in numbers and see what we get. Well, you know what? Actually, there are ways to simplify this, too. So delta y equals, if we multiply this first chunk, we get sine theta vi delta x over cosine theta vi plus, let's multiply this other piece across also, remembering that, of course, we can put the squared inside. We just have to remember now that we have to square the cosine also. So we can do that. That gets us a delta x squared over 2 cosine squared theta vi squared. So what are the first things you can do to simplify here? Who sees something that can be canceled? Vi in the first expression. The reason that I'm encouraging you to look for these things is we'll get into problems where, oh, they don't give you a Vi. Oh, they don't give you a whatever. And so you have to be able to manipulate it algebraically to look for places where you can cancel things out. Okay, so sine divided by cosine, we're not even going to get into trig identities, but at this point we have delta y equals sine theta delta x over cosine theta plus a delta x squared over 2 cosine squared theta vi squared. Okay, I don't see anything else. I mean, we could factor out a delta x, but there's really no point in doing that. So we're probably, there will be points when it is necessary. We're probably at a point where we can plug in and go. So we should have something that looks like that. Be really careful with your signs here. Remember that you're going to end up adding a negative. Raw answer for delta y? What do you have? Go. You don't have a raw answer. You were just BSing me. Okay. We've got this for a delta y, 3.77 meters. What does that mean in terms of answering the question? So it means that at 10 meters, that is the amount of change in the position on the y-axis of the dart. So if we take this whole thing, copy, blow it back up, the dart ends up, this is the 1 meter mark. The dart ends up, this is the 5 meter mark. Of course, we're treating the monkey as a point, which it's not. But the dart ends up 4.76. How many sig figs do we have? 3? Yeah, we have 3 sig figs. So the dart ends up at 4.76 meters above the ground. Now the other question is, does it hit the monkey, which I don't really care about. That's the least interesting part of it. How would you figure out where the banana is at that same time? You'd have to solve for time. At what point in time is the dart here? And then you'd have to use kinematics equations to just do straight free fall for the banana. That's an easy one. I mean, the punchline giveaway, yeah, it hits the banana. Oh, isn't that cute? I don't care. The banana's very sleepy. But these are really what you're doing, is looking at a whole picture and solving for these. Even if you are not completely done with horizontal projectiles, I want you working on these today. I'm going to give you a packet, probably at the end of the day today, but I want you working on the book problems for this. 1 through 5 on page 104. Okay. 1 through 5 on page 104. That's it.